Okay, so welcome. This is the inaugural meeting of Math, I believe 398. I think we call it the Independent Studies, ending with an 8 if it's the spring and a 7 if it's the fall. The title of the course should be something along the lines of Operations Research, Linear Programming, something in that general flavor. I know some of you have taken a version of this class with me before, some of you haven't. Everybody has very different backgrounds. The purpose of an independent study is for you to explore topics that will be relevant, that will be of a high value to you, either in your career at Williams or more likely beyond Williams, that are not really met in the normal curriculum. So I realize you're all coming from different backgrounds. That's great. That's fine. You will get to meet each other and find out your backgrounds, because independent is the first word of the class. Right? It's not the standard lecture class where, sadly, I will be able to give you 3 lectures a week. So I will talk about some problems in great detail. We will plan on 1 major lecture each week. The themes are going to be on efficiency and optimization. So I know some people here were involved in the recent LEGO Winter Study, where we found a very interesting way to explore efficiency and optimization issues. And so there will be another attempt. Funding is being arranged right now as we speak. And so if people are interested, that is definitely something we can do. I thought what I would do right now is just talk a little bit about some of the topics I want to pursue, and then if there are topics you guys want to pursue, just shout out. If you want this to count as a stats course, that is possible. You just have to make sure your final project has a stats-heavy component. Right now, a version of this class will be offered next fall. So again, if your schedule is too busy to take this now, don't worry, you can take it in the fall, but you will be stuck with the same instructor. So you're not going to be able to improve that by waiting, unless somehow I miraculously learn a lot about teaching in the next, could happen. Okay, so the question is what to study in a class like this. And so one of the things after I go through what I want to do is I want you to tell me what you're thinking of doing post-Williams. What do you think would help you best post-Williams? What do you want to learn that we can somehow link to a class titled Linear Programming Operations Research? So that gives us a lot of stuff to play with. And so how are we going to do this? Well, I will be lecturing on some subjects. You guys will be lecturing to yourselves and to me on some of the subjects. There will be a major project that everybody will have to do. Everybody's going to have to do some amount of programming. I don't care what system it's in. If you want to program in Fortran, go for it. But I want you to be able to put on your CV that you were able to program problems of importance. This is a good, useful, marketable skill. Those are not bad words. Okay? I want this on your CV. I want this when you're talking to recruiters. I want this something you can describe. Conversely, if you decide to do the highest calling possible, become a pure mathematician, it is still worthwhile to be able to know how to write programs and just how to investigate things. I have a paper I'm working on with a couple of former small students, and there is a mistake somewhere in the theory, or the rate of convergence is extremely slow, and the 10 millionth Fibonacci number is not far enough along to see the convergence. We're off by about 1 unit. So there's a small algebra mistake somewhere that the simulations is pointing out. And it's good that we're finding it, and it's good that we're going to have the final version of the paper be correct. It's not fun right now, but this is one of the reasons, even if you're becoming a theorist, why you need to know how to write computer code. You need to gather data, and you need to get a sense of what's true, what's not. Alright, so let me just go through a couple of the topics I found interesting that I want to discuss. Ancient classical algorithms. So I chose 4 things from that, and I'll write on the board. I think this is going to be somewhat visible. So ancient classical. So I guess the first question is, who knows what an algorithm is? Okay.
A series of steps that supposedly reach some end, that you follow the rules in order to.
Sounds as good as any other definition I've heard. Series of steps, a recipe, a procedure, you go through it, you crank it, you get to what you want. And so here are a couple of things I want to talk about. Babylonian multiplication. Pointers algorithm. Fast exponentiation. And Strasson's algorithm. many people have heard of Babylonian multiplication? Okay. If you've taken a class with me, there is a good chance at some point you have heard me spiel about Babylonian multiplication. So this is going to introduce us to the concept of lookup tables, as to just because you can do an operation in a certain way doesn't mean that that's the best way to do it. And again, this is one of the biggest differences between pure mathematics and applied mathematics. Can somebody give me an algorithm to determine if a number is prime? I'm assuming everybody knows what a prime number is. If not, just play along and look it up tonight. Okay.
Just go through every other prime number, divide it by it, see if it comes out. Just keep going until you get up to the number you're at.
You were so close to having the worst possible answer. You missed by one word. You said go through every prime number.
Oh, every number.
Yeah, exactly. That's much worse. Right? Go through every number and see if anything divides your number. Okay? You can make the algorithm a little bit better. Right? So one suggestion was to go through just prime numbers. What else could you do?
Only go up to the square root.
Only go up to the square root of the number. But these are still very expensive. In principle, it's trivial to figure out if a number is prime. Just divide. In practice, it takes so long to figure out if certain numbers are prime that it's not of practical use. You need better algorithms. So Babylonian multiplication, Horner's algorithm, how many of you have heard of Horner? The fast way to evaluate polynomials. So these are some classic things, and this is going to lead us into fractal geometry and chaos theory. And so, these are really big issues. It's not enough to do something, you need to do it well. How about fast exponentiation, fast multiplication? If you want to multiply x times x times x, if you want to calculate x to 100, how many steps does it take to calculate x to the 100? So this is going to lead us into different bases other than base 10. Which bases do you think the universe cares about? I can't prove it, of course.
E.
E, good candidate. What else? 2. 2 is a natural base for the universe to care about. As a baseball fan, there's a couple of other bases I'd like to think the universe cares about, but I can't quite prove it. Base 10, yes or no? Do you think the universe cares about base 10? Probably not. If you want to discuss that, there are other departments on this campus where you can have those discussions. For us, base 2, base E, these are the most natural. Maybe some of the other bases, maybe base 3. There are some things where base 3 is better than base 2. It's a little bit more efficient for storage. And so fast exponentiation, we're going to see better ways of multiplying. And this will lead beautifully and immediately into Strasson's algorithm. A lot of these things are very easy to state. You can go to Wikipedia and you can look at Strasson's algorithm, and 2 minutes later you've understood Strasson's algorithm. It's a better way to multiply matrices, much faster than you would expect. And of course the question is, well, who cares? Well, it turns out there's so many things that you can model with matrices that being able to do these operations at a much faster level has incredible implications in terms of what you can compute in a reasonable time. How big of a system can you investigate? One of the best quotes I've ever heard in my life made a real impression with me. Not enough that I remember it exactly, but enough that I can still paraphrase it. And it was when I was at Ohio State as a postdoc taking a data analysis seminar. And somebody, don't remember the name sadly, said every day the satellites above the Earth beam down more information about the weather than is in the entire Library of Congress. And the computers have a couple of hours to analyze it for the weather predictions. So how do you handle that much data? And so sometimes even small improvements in the exponent, replacing matrix multiplication as an n-cubed algorithm for n by n matrices with n to some number less than 3, has great applications in terms of what you can do. So, the first part of the course is I'm going to just start off, unless there's major objections, with just going through some of the algorithms like this. Giving you some assignments to do, having you write some code to actually implement some of this stuff. And I'm not having you write the code because nobody's ever written code to implement stuff like this before. I'm having you write the code because I want you to get experience doing that. I don't care what language you use. I know some people here have a lot of CS expertise. Congratulations, you've all volunteered, and your volunteering has been gratefully accepted to help people who haven't seen programming. Okay? Doesn't matter what language you use, a lot of this you can do in Mathematica. There's even Microsoft Excel, which would work a lot of this stuff. And for some things, the advantage of Microsoft Excel is it's very portable, lots of people can easily use it. For the stats people here, what are you thinking?
R.
Yeah. As a Bostonian, I can't say that, but fortunately you all knew what I meant. Okay, any questions on some of the basic algorithms I want to do in this course? These are hopefully classical things you've all done. I mean, I am assuming everybody has done multiplication before, so that these things are not that strange, all the way going up to multiplication of matrices. There's a nice connective theme here. Okay, so we'll talk a little bit about how to do these things efficiently. So for those of you who survived my Lego course, hopefully now you can't look at anything without seeing better ways of doing it, without being, oh, how are they doing, why are they doing it so slowly like this? And so I want you to leave this class thinking about better ways of doing things you're stuck doing all the time. Okay. So the next set of stuff, I'm calling efficiency revisited. Okay. So this is a question to see who knows me really well. I think it is criminal if you take a linear algebra class and you leave thinking that you should compute a certain object a certain way. Anybody know?
Computing an inverse with,
Not inverse.
Eigenvalues?
Eigenvalues, yes. How is it criminal? You should be prosecuted for this. How do you normally compute eigenvalues in a linear algebra class?
Solve the determinant.
You solve the determinant equations. So eigenvalues is the first one. The second one is difference equations. The third is binomial coefficients. Is there a fourth? There's a fourth, sorting. And for those of you at the colloquium today, we talked a little bit about sorting. And then the fifth is factorization. Okay. So these are, 5 topics that I would like to revisit. And so, determinant of a minus lambda I equals 0, yes, theoretically this is a wonderful way to calculate eigenvalues. We can prove a lot of nice theoretical properties. Why would this be a nightmare to do in practice?
It's not easy.
It's not easy. I mean, if you just do it naively, you've got a polynomial of degree what?
Yeah.
So to do determinant of a minus lambda and expand it out, how many terms are there in the determinant? Not n.
No.
If it was n, it wouldn't be so bad. You have to look at all the different permutations. It's n factorial. Now we can do tricks. We can bring the matrix to upper triangular form, so it's not so bad, and then that will be a polynomial of degree n. You'll only care about the diagonal then. But you then have to solve horrible, horrible stuff to work with the determinant. So how else can we calculate eigenvalues? So again, I want you to revisit things you've seen many times and try to look at them from a different vantage. That I need to be able to do these things quickly, and I need to have some control over my numerical accuracy. I've got to control my rounding errors. How much will these errors make a difference? And so as an interesting example, you can look and see how stable your solutions are if you change values of certain parameters. And so this is where some statistics can come in. If you just randomly push a bunch of the entries, how much does that push the roots? Does it push them all a lot? Does it push them all a little bit? Do you have some kind of continuity? The next is difference equations. I know some of you have seen stuff like this with me, like Fibonacci numbers. So I can write down a recurrence relation. Fn plus 1 is Fn plus Fn minus 1, give you some initial conditions, and you can calculate all the Fibonacci numbers. The problem is if you go from the very beginning, if you want to calculate the millionth of the 10 millionth, you have to go through all the numbers to get there. Are there better ways to just jump? So how many of you have taken differential equations? If you don't want the camera to see it, just raise your hands low. How many of you have taken differential equations? Okay. Yes.
Well, I never officially took
Okay.
it, but I go online. To
Okay.
take a look.
Okay. So at most we've had 2 people express some amount of having taken the differential equations. So we will talk about solving differential equations and difference equations. We'll talk about numerical stability with these things, the mathematics behind something like this. And how can you quickly come? And so we might, deciding on how much we want to go, we might go into some of the numerical integration and numerical differential equation methods and just to see how would you solve these, what would be the errors, how would you analyze stuff like that. Binomial coefficients. I'm assuming everybody has seen binomial coefficients. These are the in choose k, these are Pascal's triangle. Okay, everybody has a homework assignment for Tuesday. I won't be in class to collect it, but I can still give you a homework assignment. I want you to draw Pascal's triangle, and I want you to draw as many rows as you feel you need to understand what's going on. And then I want you to take Pascal's triangle and redraw it, and put in a filled dot if it's odd, and an unfilled dot if it's even. So Pascal, filled dot at odd, unfilled spot if even.
What do you mean by that? Like uphill version?
So you could do this. So it's 1, 1, 1, 1, 2, 1. So maybe like this. And you leave it blank or put it
Oh
in.
yeah.
You get
I
to
know
choose. So if you've seen it, don't say anything. Okay. So I want you to just do this and see what pattern emerges, if a pattern emerges. Try to prove the pattern that you're seeing. And if you want to write a computer program to do this, how would you write a computer program to quickly draw a huge amount of Pascal's triangle mod 2? So how many people here have not taken abstract algebra? It's sad that the camera's going to get this, but I haven't taken abstract algebra. So all we really need here. Look, this is why it's an independent study. If it was a regular class, they'd make sure you had a professor who was well qualified. It's a little slacker for independent study. So what we're really doing is we're doing clock arithmetic. I just care is the remainder 0 or 1 when I divide by an even number. If it's 1, I fill it in. If it's 0, I leave it unfilled. And so how many rows do you need to do before you can see the pattern? It's a function of how well you can recognize patterns. But how would you write a computer program to do this efficiently? And so I've written a program to do it unefficiently in Mathematica. And I'd like to write a much better program to do this extremely well and generate a huge number of rows. I tried to find a good video of the triangle being formed on YouTube, and amazingly I have not found one yet. So if people want to do some searching and see, but only do it after you try to do it. I want you to try to sniff out the pattern and see if you can figure out what the pattern is. The next is sorting. So for those of you who have taken some CS classes, you'll have heard of things like merge sort, bubble sort, quick sort. We saw a new version of sort today. We saw stack sort at the colloquium talk. And so I want to talk a little bit about the different ways of sorting. One of the reasons I want to talk about it is a great introduction to complexity theory. And in terms of what metric are you going to use? I've got to be very careful because this is being recorded. I will gamble. I was asked to review a paper for a journal, and the paper had a discussion on whether or not somebody should have won the MVP. And they were talking about different metrics you can use to determine if they should have won who should win the MVP.
Which sport?
Baseball.
Which year?
2012. The Cabrera Trout year. And so,
Sorry, buddy.
no problem. So, the paper never returned back to answering the question after they developed new statistics, which I thought was quite bad. But the Cabrera Trout MVP, so I know we have a couple of baseball fans here. Sadly, the tendency of this class is, I think, leaning towards the dark side. But how many of you are familiar with the Cabrera Trout fiasco from 2012? So, Trout, if you believe in the sabermetrics, if you believe in all the math baseball formulas, was the more valuable player than Cabrera. But Cabrera he crossed a psychological barrier, he crossed a key barrier. No one had won the Triple Crown since Carl Yastrzemski from the 1960s Red Sox. And so, you take away 1 or 2 home runs, I forget exactly how many you had to take away. If he hadn't won the Triple Crown, it would have been Trout in a landslide. But just the fact that he got those 3 statistics, which are not that meaningful, gave him the Triple Crown, and that gave him first place vote and MVP in a lot of people. So depending on what you choose as your metrics, you will get different answers. So when we analyze the sorting algorithms, what I like about this is different metrics will have different algorithms win. So when you're trying to see which sorting algorithm works, I'm going to give you a bunch of numbers, and I want to sort them. How do you think I should determine which algorithm works better?
I think whichever one asymptotically the quickest.
Okay, so which one is asymptotically the fastest? And what do you mean by asymptotically the fastest?
Like you can sort of determine the complexity of an algorithm, like how it generalizes to like n sample, and
Be very specific. So how are you telling how complex it is? What are you looking at?
you're looking at like the runtime of the algorithm dependent on some number of input, like when you're trying to see compare it to some other you want to compare it to some baseline and see if it always sort of exceeds or
So I have two algorithms,
yeah,
and what am I comparing them on?
like the same input,
How many inputs?
and it varies.
You gotta be a little bit more specific. You gotta be very specific in this game. If you're not completely specific, so I want to know which algorithm is better. Which algorithm sorts faster? What's my definition of sorts faster? Yes.
Like how many iterations of the algorithm it takes to get to the desired goal.
On what input?
What? Excuse me.
On what input? You have to be more specific.
Sorry, I don't quite follow.
You need to tell me what you're comparing. I have two algorithms. What am I running them on?
Computer.
Not specific enough. Am I running them over?
If there are n numbers you're trying to sort, then you look at how many times you actually check the number.
So am I looking at a specific set of n numbers once and only once?
So it's like if you have any n numbers, then when you compare the two algorithms, you look at, for example, the first algorithm check each number twice in order to sort everything, and the other one check each number n times in order to sort everything, then the first one is better.
But maybe my first algorithm runs better on some inputs and worse on other inputs. So you gotta be very careful. So you're talking about the average runtime? If I look at all n factorial arrangements, do I see on average how fast does my algorithm run? Do I look at best runtime? What's the fastest it runs? Do I look at worst case scenario? Worst case, how bad is this algorithm? Do I look at median runtime? 50% of the time it will run in this amount of time or less. There's lots of different ways you can define what you mean by the speed of an algorithm. If I tell you exactly what the input is, okay, that's not so bad. But when you don't know what the input is, well, what is the space the input is coming from? So there are some algorithms that will work better on some types of inputs than others. And so when we analyze the sorting algorithms, when we start talking about how efficient is one of these algorithms, it's going to depend on what we're applying it to. And so some solutions are to say, well, let's let all n factorial possibilities be equally likely. And maybe you have an algorithm that works really well most of the time, but very poorly every now and then. And then how do you want to rule things out? Maybe every 10 to the 200th times it comes across something that it can't solve, and it hangs up, and the runtime is infinite. Well, okay, then that algorithm will lose to a very poor algorithm. But the likelihood that you're going to get one of these 1 over 10 to the 200 is so small. So we'll talk a lot about metrics when we get to sorting. And this is an extremely important issue. If you can't agree on a metric with somebody, you can't really compare and say who's better or who's worse. And this is one of the big problems with things like the MVP or voting in college football. Different people have different standards as to what they're voting for, what they're viewing. And they will get to different answers from the same input. So I think there's a lot we can learn by discussing sorting. Factorization and primality testing is a wonderful thing. Enormous applications to cryptography. So a lot of mathematics is built around the assumption that there are certain processes which are hard to do one way without a backdoor trick. So we don't have to go into too much technical detail. If I tell you n equals x times y, can you factor n? I'm telling you n equals x times y.
Yeah.
Okay. So everybody agrees that if I tell you n equals x times y, you can factor n because I've just given you the
Depends on
factorization.
what, yeah.
What if I tell you n is a product of two primes, n is product of two primes, and prime p divides n. So now I'm not telling you the factorization of n, but I'm telling you one of the two factors. Yes, not so bad here as well. So there's a lot of mathematics like this where when you have a back door, it's very easy to finish the calculation. It's believed right now hard to factor a number without having a back door. There may be a way to do it. There have been other algorithms that have been used for cryptography that were thought to be hard without knowing some secret special information that only later did it turn out they were easy after all. And so we'll talk a lot about factorization and primality testing. What I love is there's certain tests for primality that will tell you if a number is prime without telling you any of its factors. So it seems very surprising. I can guarantee you this number is composite. Oh, I can't give you a factor of it, no, but I can tell you it's composite. And we can do these things quickly. And in fact, doing this is actually going to be related to the fast exponentiation we talked about earlier. I know people have to go in and out. I will post this online later today, so whatever you miss, you can just grab from there. Okay. Any questions on this part of the unit? Okay, now it's time to get to the core part of the class. I don't know why I'm so concerned about saving that chalk line. Linear programming. So there's a lot we can do with linear programming. So the first is we'll start off with the basics. And so the basics mean things like the diapole. This is one of the original applications of linear programming. Let's say you don't care about how things taste, which depending on where you go to school, that can be a very useful survival skill. All you care about is making sure you get enough calories to stay alive. And different food, well, calories and nutrients. Different foods have different nutrients. And you want to know what is the cheapest way to stay alive. Or maybe you're a dictator of a small Asian country. Don't care so much about your people, your uncles, stuff like that. You just need to make sure that people stay alive. Okay? How can you do it as cheaply as possible? So it turns out this is a great thing for linear programming to solve. And so there are certain problems like this where the solutions are drawn from a continuum, where linear programming is great, it's fast, it's efficient. If you go to the supermarket, how many of you have ever seen the movie Father of the Bride? Have you seen it?
I definitely have, but
Steve Martin?
yeah.
Okay. Okay, so Steve Martin is the father, his daughter is getting married, and the wedding is just spiraling completely out of control. And there's one scene when he just loses it in the supermarket. And he just is furious that hot dogs are sold in one count, and hot dog buns are sold in another. And so what he does is he starts ripping open the hot dog buns and starts throwing buns out because he wants the number of hot dog buns to match the number of hot dogs. You cannot do this without getting into trouble, as he quickly finds out. And I think they sent him to jail for the night. Okay? It's a very great scene. You can't go into a supermarket and start doing this. But there are many things where we can assume you can buy things in a continuum. You can buy however much of this food you want. Or we're trying to figure out, we have a bunch of oil refineries, we have a bunch of cities that need oil, we want to ship the oil to the cities, we want to minimize cost. A lot of these things we can do very easily. And we can do them because things are coming from a continuum. There are things that are a little bit harder. In a few weeks, spring training will resume. Baseball will happen again. It's going to be a good time. What's the first thing that really comes out for baseball season?
The worst thing.
First thing that you really find out about a baseball season, or one of the first things you got to find out about. Schedule. So you've got to make a schedule. Right? The schedule's going to have lots of constraints. Can you have half of your team play the Orioles and half of your team play the Rangers on the same day? No. If it's spring training, yes, they allow that, but for the regular season, you don't split up your team. Your whole team travels together. Your whole team plays together. You're either playing a team or you don't. It's no longer a continuum. It's now integer valued. And so this whole idea of going from a continuum of possibilities to a discrete, separated set of possibilities causes enormous trouble. We do not yet know good ways of solving all integer programming problems. And so for those of you who've done some computer science, this leads into the P versus NP. And so we'll talk about stuff like that. So the next thing after we do the basics of linear programming, we'll talk about the simplex method. And so the simplex method is a beautiful way of solving linear programming problems if we have, real valued quantities, if we can vary things continuously. But when we get to the discrete stuff, we no longer have the power of the simplex method. We do have other techniques, which I would love to explore depending on how people's stuff is. So one of them is binary integer programming. So in binary integer programming, everything is either a 0 or a 1. It happens or it doesn't happen. So your first question is this restrictive? If I consider just binary versus more general integer programming problems, if I can do integer programming, can I do binary integer programming?
You should be able to, because you can represent all.
Well, so wait, be careful which one I said. If you can do integer, general integer, can you do binary? Yes, why?
It's a 0 and 1.
It's a subset.
Yeah.
Right, that way is trivial. Right? If you can do integer, you can do binary. Okay, now what about the other way? If you can do binary, can you do integer?
Not necessarily.
So that's not as clear. So can you solve a general integer programming problem where the outputs are integers if you can only do binary programming? Any thoughts? No?
I mean, I would assume so,
Okay.
because it's been done.
Mm-hmm. So what's the trick? How can we pass from being able to do things binary to doing things in general?
You have to define the binary outputs, 0 and 1,
Okay.
in a way that actually relates to the general integer.
So can you get every integers from just binary operations from just zeros and ones?
Some combinations of them, if you do repeat it.
Yeah.
Right, so what's the key word I'm looking for? Or the key phrase? So it's really, I'm sorry?
You have to repeat, to do several repeated
Right.
programming problems.
So there's a good phrase for what you're doing.
Recursive.
Not recursive.
Lather, rinse, repeat.
Not lather, rinse, repeat.
Okay.
So what do you call the 10 fingers of the universe? Digits, right? And you call it decimal expansion. And you can write any number in decimal. Okay? If it would help, I can see if I can chop off your fingers. I don't know if Williams will let me, but we could put on maybe some super mittens, and you just reduce it to the 2-fingered hand, right? And so if you can expand something in base 2 in binary, then your number, your general integer, can be written as a sum of binary variables with just different blow up weights, these powers of 2. So it's actually sufficient to be able to do binary to do general integer. And so it's just a question of what's the easiest way to work with the available software. So for this, I really don't want you writing software to do binary integer programming problems, but I think it would be a really good exercise, really good line on the CV to write some programs. And so last year when I did this as an independent study, my students did a phenomenal job and they solved a real world problem for a school district. They got paid, and I think I still owe them a dinner.
Yeah, you do.
I do, yes, we still have to find a time for a dinner. And so my mother has a problem that she would like solved. So she sometimes plays bridge, and this is being recorded. Hello, people who play bridge with my mom. And I'll use better phrasing than the phrasing she gave me. There are some people who are just such wonderful people. You want to make sure you play with these people as many times as possible. But of course everybody wants to play with those people. And so, is there a way you can maybe make sure that nobody plays with anybody too often? So that, one person isn't fortunate enough to get to play with this wonderful person again and again and again and again and again. Can you come up with schedules to make sure something like that doesn't happen? So that you share the wealth. Okay? So my mom would be very happy if that's finally solved. Okay? So we can try to find some real world problems. Other good places is looking at school districts that are trying to figure out, scheduling. And so sometimes they're even trying to figure out what the league affiliation should be. and they need to minimize travel times, but they also want to make sure that the matches are competitive. If the schools are too mismatched, it's not going to make sense. And then the last one I want to do is stochastic programming. So how many of you are thinking of taking this as a stats course? Okay. If you're thinking of taking this as a stats course, as I said, the final project has to be stats heavy. And then you will have to make sure you do stochastic programming if you're doing this as a stats course. Or if you've already taken linear programming with me, you've got to make sure you do stochastic programming. If you're not taking this as a stats course, you should still do this. Okay? So in the real world, the course description I have, I think, was beautifully phrased. In the first N math classes of your career, you can be misled as to what the world is truly like. How? You're given exact problems and told to find exact solutions. The real world is sadly more complicated. Frequently, we cannot exactly solve problems. Moreover, the problems we try to solve are themselves merely approximations to the world. So here's the difficulty. I want to try to model the world. Well, I need parameter values for my model. I don't know these parameter values perfectly. And so I don't want to get too hung up of trying to solve exactly an approximate model. And so then the question becomes, stability issues. Or what's my best guess? How much of a tolerance for risk do I want to take? When I'm trying to figure out what is the optimal solution, well, if I don't know the true values of the parameters, how many of you are thinking of having a useful career where you work in industry and actually do something? So this one I don't mind. My father took a class for his master's where he was given an equation with somewhere between 46 and 52 variables to tell your company what to do in given situations. And the professor was super theory woman. And he tried to explain to her that not only does he not know the value of a lot of these parameters for the competition, he doesn't know the value of these parameters for his own company. Effectiveness of marketing. We have guesses for how effective our marketing is, but we don't, how stable is your formula as we vary these quantities that we don't know exactly. And so in stochastic programming problems, we take the situation where we don't know the exact values of these parameters, and we want to try to get a sense of what can we say about the solution? What can we say about our strategy in a situation like this? Right. So these are the main things I want to do. How many people are considering math grad school and becoming a purist? Okay, I'm sorry, that's past tense. Considering or considered. So one of the things I would strongly urge you to do is Kepler's sphere packing conjecture. So Kepler's conjecture was formulated before Fermat's last theorem, and the proof came after Wiles' proof of Fermat's last theorem. So it was unsolved, open longer than Fermat's last theorem. And the simplest way to say it is, imagine you have a bunch of cannonballs, perfectly spherical objects. What is the most efficient way to stack them so that you have the least empty space between them? And the solution, we knew for hundreds of years, is basically hexagonal packing. Where you keep taking a bunch of hexagons, and in each hexagon you put a sphere. Come down here. Then the next level you put the sphere over it, so it goes into that hole. The way your grosser packs things. But it took hundreds of years before people came up with a rigorous proof in 3 dimensions that this is best. There's also, of course, analogs of this question to higher dimensions. The solution that Hales used for this involved computers, and involved computers doing linear programming. So it was a monumental tour de force that he was able to get this down to a linear programming problem that could be done in a couple of years' time. And so this is something I would really like us to talk about and have at least 1 or 2 people going deeply into the mathematics behind making this accessible. And again, it's not enough to have a problem that's finite. You need to have a problem that's finite in the amount of time you have available to do it. Just checking to see where we are on time. Oh, perfect. So, Kepler's conjecture is another great thing to look at. It leads into all the difficulties of how do you trust a computer proof? Well, I've seen plenty of my colleagues. I don't know. I trust a human proof. As which do you think is more likely to make an error, a human or a computer? What can you do to make sure that the computer is going to give you the right answer? What kind of test cases can you do? But it's very easy to miss a case. It can happen either with pen and paper, or it can happen on the computer. And so this is a great thing to look at as to how you do this. For those of you who really are not that concerned initially with packing 6-dimensional spheres, or 18-dimensional spheres, these have applications to cryptography and efficiently transmitting information. So you can look at various spaces of codes and sequences, and you want well-separated objects, so that you can identify if there's been a change, if a digit has been mistransmitted, what was the digit that was meant. So these are called error-correcting, error-detecting codes. And so that's one of the wonderful applications of sphere packing. Okay, so these are the main topics I was thinking about studying. Again, there'll be one lecture a week where I will pontificate on the board. I will record these because I know not everybody's able to make it at the same time. It is not quite the same, watching it on YouTube from a camera like this as coming live. I have tried to find as much as possible a time that works for everybody. The only guaranteed way to do that is to take a time either everybody absolutely hates or to kick people out of the class. I really don't want to do either of those options. So if you can't make the times, I apologize. I can see about maybe occasionally swapping, so maybe we have 2 key times that we go between, so that similar to my mom and her bridge partners, no one gets the joy all the time. Yes?
I'm sorry, what are the times?
So right now I think we have Tuesday 9:55 to, was it 11:10? I think that's the block.
Yeah.
Okay, we've got about another 5 or 10 minutes in this room. So the way the class will work is, again, once a week I will lecture. I would like people to get together maybe once a week for lunch where we can just discuss things. My schedule, I am extremely overcommitted at this point, and so, I don't get credit for Williams for doing this. I do this because I want to. I do this because it's fun. I do it because it's a good service for you guys. But I've got to try to find a way to get it to work with my schedule without overloading me and without affecting the standard classes I have. And so, if you're not able to make the lunch, that's fine. We can try to do other things. We can try to do one every now and then, just meeting in my office, meeting down in Eco Cafe, something like that. But I need to try to find meals for me are very good. I'm supposed to eat at least 2 or 3 times a day. That's a good way to get a meeting in. Everybody has to do a project, okay? Everybody has to do a project with either nobody else or at most 20 people, okay? I really don't encourage groups of more than, I'd say for a class like this, 3 people. Probably groups of 1 or 2 is the best way to go for this. If you really want to do a group of 3, talk to me. But you want a chance to really delve deeply and master something. And then at the end I want you to present. So I want you to get practice in giving talks. Now what's nice is when you give a presentation to the class, you'll be talking to people who have been going through the material with you. They will have a good background, but they may not have the same background as you. They have not been thinking about things as deeply. How many of you are not seniors? So this is practice for colloquium among other things, right? For those of you who've already survived your colloquium, you still have to do it. But you're experts. Now it's no problem for you guys to do a talk. Unless you're going to be a mime, you will almost surely have to present information to people. If you're a mime, you still have to present information, you just have to do it in a different way. It's a good skill to learn. The American Math Society is interested in publishing a book based on this idea for a course. And so what I would hope is that the projects you're working on and the stuff I'm doing will become the nucleus of a book and will become the nucleus for the course next year. There's enough people that we can take turns. We will just rotate, and I think everybody will be in charge of taking up really good lecture notes for one lecture. Not this, screw this, but everybody will have at least one class where your job is to write up everything in great detail. That means including jokes, it means adding illustrations, it means making it a complete set, it means adding homework problems. Okay? This way, you're going to get a great line on your CV. You will have a non-trivial involvement in a book. And I will deal with the AMS in terms of how we will do compensation for you guys for something like this. Any other general questions about the course? I'm going to stop the recording now so we don't have anything